So this is day 2 for our harmonic oscillator chapter, kind of an extra fun little chapter we're doing now that the main part of calculus is wrapped up. Before we get too far into today's work, which isn't very much, there's just 2 pages of theory and 2 pages of practice. But let me just talk about the last video that was online, that lesson number 1. As you probably know by now, I had some troubles because YouTube, probably rightly so, was a little bit upset that there was some music in the video and it was worried about copyright. So I had to actually put it in with the music either totally turned off or with it reduced to a really low volume. Unfortunately, it's a really cool thing where you really need the music. So if you take a look at that all resources folder that I've got, I have put 3 files in there that if you haven't seen yet, you really should go and take a look at. They're worth your time. In the middle of that first video, when I was just sort of saying, hey, here's how you can pick up with one part of the song to do your counts. This is a video you can watch to go and see just what that kind of counting process looks like. That's where I had to have the music turned way down. And then I think the best part of all of this, the reason for doing it, is actually this section right here, these little tests where you actually get to try it out. Okay, and so that's where I was trying out putting the right mass of water in the can to get it to dance to the music. Absolutely worth your time. I dare you to watch those and not giggle. It's actually kind of neat when you can get the mass just right. And that's actually going to be your goal for one of the 2 little, I'm going to say assignments, but I'm doing air quotes here because it's a kind of a fun little thing that it's entertaining and you're going to want to do it. And that's kind of down the road. I'll explain it at the end of this video, and then there's some time a couple weeks from now to actually do it. And it probably won't take you more than about 10 minutes or so. But definitely worth watching those videos if you haven't seen them yet, because the sound had to be cut out in the original one online. So here we are. We're going to look at a couple more kind of technical aspects of the math and then practice that a little bit, and then I'll give you a bit of a lead in for what the assignment for a couple of weeks down the road will look like. First example says, hey, see if you can find a solution to this differential equation. Well, when I first look at it, it does look like that differential equation we were playing with the other day, where it's 2 derivatives deep, and then there's the original x in that answer there. I would probably rearrange it and say, okay, it looks like x double prime would actually be negative 16x. Now, I don't know the backstory to this. I don't know, like, well, where's the spring? Where's the mass? They're just jumping right into it and saying, oh, well, here's the differential equation. So if I was to compare this to what we were looking at last day, it's like we're a few steps along already, where last day we would say, oh, well, the second derivative of x for the harmonic oscillator would actually equal to negative k over m, spring constant in the mass, multiplied by x. So it looks at this point like they've already done some work, right? And they've said, oh, well, this k over m, we've already figured that out for you, and that's actually equal to the 16. So I'm going to pick up right from there and see where we can go with the math for this. Looks to me like this probably was a harmonic oscillator with k over m equal to 16. And then what we saw last day was the bouncing rate expressed in kind of a Math 12 radian angular velocity, this omega. So it's not a w, it's actually the Greek letter omega, lowercase omega. That's equal to the square root of k over m. So it's going to be the square root of 16. Oh, how handy is that? Nice perfect square to take a square root of. And so we get this angular velocity, this bounce rate of 4, and it would be 4, it's very trig-ish here, 4 radians per second. Okay, well, I know generically, we call this the general solution, that the generic general solution for a bouncing mass on a spring is some constant multiplied by the cosine of your bounce rate times time. So in would go this 4 times t. And then there's another potential term there, b times the sine of the exact same bounce rate. Okay, it's going to be that 4t. So just taking that number, putting it in there. Now, how do you find out what these values for capital A and capital B are? They totally depend on the release. And the release is actually explained here. It says, well, at the beginning of the day, we're going to hold this thing at position 2. So it's actually 2 units above equilibrium. Oh, wait, also at the beginning of the day, we're going to throw it downwards at 12, right? It's got an original velocity, right? That's all that x double prime is, right? This is just trying to say, oh yeah, there's going to be some velocity here. It's going to be at time 0, a velocity of negative 12. Well, we saw last day how you can figure out these values for A and for B using those things. The value for A is indeed just equal to the original position. So it looks like the A has to equal, in this story, 2. Okay, so we're going to be able to substitute that in just a minute. And the B, well, you'd have to take a derivative of that A cos 4t plus B sine 4t, and the 4's would show up, the omegas would show up. And so what we said last day was that actually omega times B, because an omega would show up, the 4 would show up, that's equal to the original velocity. So 4 is our omega, multiplied by B is equal to this negative 12. So it looks like the correct value for B to use, that describes, it deals with the fact that there's an original velocity, is negative 3. So here's the answer. The specific solution, so it's not general anymore, it doesn't just have a big A and a big B sitting there. The specific solution for this story, based on the way that it's thrown, is 2 cosine of 4t, and then it would be plus a negative, or you could call it minus, whatever you want to call it, plus a negative 3 sine of 4t. So I'm going to take a second and actually just graph that, just to kind of see what it looks like. I want to make sure that, this thing does indeed bounce, and that it actually starts where it should with kind of the right velocity as well. So I'm going to just put this into my equation here, into my y. I'm going to go with 2 cosine of 4t. So as you know from your Math 12, that'll affect the bounce rate. I say t, but I'm typing in x because that's how my graphing calculator wants to use it. Minus 3 times the sine of 4 times my time, and I'll use x for time. So I'll use y for position and then x for time. Okay, now my window. I want to go for times, maybe from 0 to, I don't know, not too sure. Let's try we'll try 3 seconds at the beginning. Let it bounce for 3 seconds. My y min and y max, not really too sure what the best choice here would be. I'm going to try maybe negative 4 to 4. Okay, I'm not really sure how big this thing is going to bounce because it's got a big velocity there at the beginning. I might need to expand that. And let's just see how this goes. See if it does indeed bounce. Okay, there it goes. It's bouncing. Oh, actually, I made a pretty good guess on those negative 4s to 4s. So this thing, it's really cool. The math is actually describing a bounce, right? It says, oh, hey, I don't know if you know it or not, that thing's going to be wobbling back and forth forever. Now, a couple of things I can check out. Let's see if this thing starts where it was supposed to. If I go, hey, calculate a value at time 0, right? And it says, oh, well, the value there is 2. Okay, that's exactly what we wanted because this story said we have to begin at position 2. Now, let's check if that original slope is correct. What if I say, hey, can you calculate for me a slope, right? That would be velocity right at time 0. And I say go. And to the best of my calculator's ability, it's saying, well, I got a slope here of negative 12. So this thing begins with a speed of negative 12. And it's got so much velocity downward that even though it starts with this amplitude, if you want to call it that, of 2, this original position of 2, it descends way below negative 2 because of all that speed, that kinetic energy it had. It goes down pretty close to negative 4, right? And then back up to almost 4. So one of the things that I'm kind of noticing is I can't quickly look at this result that we had for the question, 2 cos 4t minus 3 sine 4t, I can't super quickly look at it and say, oh, did you know it's going to bounce this much? This will be the overall amplitude up and down. And I want to show you a neat little way with the next example where you can actually see how much it'll bounce just by looking at the equation. So example 2, a spring with 2 kilograms hanging on it has a natural length of 12.5 meters. Okay, so it's just kind of sitting there hanging, maybe from some sort of support, right? So there's the roof, and this spring is just sitting there with 2 kilograms on it, right? That's the equilibrium position, and it looks like it's 12.5 meters long, right? So this whole thing just sitting there like that, 12.5 meters. Great. An additional force of 16 newtons down lengthens the spring to 13 meters. Okay, the force is released, it's taken off, and then we're going to start the strike. So you look at it, you go, why are you doing this? Why are you applying a force only to take it away? So this line here, at first glance, it perplexes me, right? Like, what are you doing grabbing the spring and pulling down on it with a 60 Newton force? And the reason why they're doing that is they're saying, well, here's some info you can use in order to figure out the spring constant. So when you pull down on it with 16 newtons, then that 2 kilograms just goes down a little bit, just down, oh, it looks like half a meter from 12.5 down to 13 meters. So when I go to find this spring constant, yeah, it's great that they're telling me, oh, well, here's a story. We're going to apply 16 newtons on it. Okay, but how much did it extend, right? What was that change in x? Well, we are now 13 meters long. We used to be 12.5, so it looks like it grew by 0.5 meters. So this is a neat thing you can do with Hooke's law, is you can do these little changes where you add a little more force and then you see that you get a little more extension. So kind of think of it as, oh yeah, there was already some gravity force on the 2 kilograms, but we increased it by 16 newtons. And that increase in force is going to cause an increase in the x. And so we added 16 more newtons, kind of looking for the k, and then we had an extension of 0.5 meters. And so that tells me that the spring constant here is 32 newtons per meter. And then they went and very carefully removed that 16 newtons. Well, that was nice of them because we don't want it to mess up our story. So I'm really thankful they did that briefly, just so that we could go and see what that spring constant is. Then they took that 16 newtons off, and they said, okay, now we're going to make it bounce. And they're actually going to stretch it down to 17 meters before they let it go. But before we do that, we're going to try to find the omega and the F value for this oscillator. So the omega, the math description of how fast it bounces, it's just the square root of k over m. So I'm going to go with the square root of 32 divided by 2. So I have a square root of 16. Okay, one more time, I'm going to end up with this value of 4 radians per second. Okay, that's all very nice. And now the frequency in kind of a physics 11 sense. Well, I know that omega is equal to 2 pi f if I want to go back to that physics 11 world. It's actually nicer not to bother, but if you want to, looks like we've got an omega bouncing value of 4. 2 pi times the f. Just make sure you divide by 2 and by pi. And when I tried that out, I got a physics 11 frequency of 0.6366 hertz. So radians per second is one way to talk about how fast it's bouncing. You kind of think of it, instead of bouncing up and down, you think of it as spinning around in a circle. The physics 11 way is 0.6366 hertz. Okay, now before I go over to the next page, it talks about the release. It says somebody grabs it and stretches it down until this spring is actually going to be 17.5 meters long. Well, this spot right here is the equilibrium position. And now somebody's going to take this spring and go, whoa, and stretch it way out until the spring is 17.5 meters long. So it looks like if this location is x is equal to 0, our 2 kilograms is below that. And just thinking about the numbers, 12.5 and 17.5, it looks like we're going to be starting off 5 meters below equilibrium. Okay, that's what that tells me. So it's kind of a convoluted way there, but when you stretch this thing to 17.5 meters, yeah, indeed, they're actually saying, okay, think about where it is from equilibrium. This thing is now beginning its story minus 5 meters below equilibrium. Okay, next page and final page for kind of newish theory. We're going to take a look at the solution for x, right? Its location, its vertical location. And the solution in general is A cosine of omega t plus B times the sine of omega t. So for all just simple oscillators, that's the relationship. The cosine term lets you have an initial position, and the sine term lets you have an initial velocity. Okay, working with those values now, I know that the A is actually just equal to the original position. So the A is going to have to be -5 because you're 5 meters below equilibrium if you stretch that spring out to 17.5 meters. The B, once it's multiplied by an omega with a derivative, that's when you get original velocity. So it looks like that omega value, which we know is 4, right? So we have 4 multiplied by B, has to be that original velocity. And they did mention it. They said, oh, we're going to start with an original velocity, there it is there, of positive 12 meters per second. So that has to be a 12. Okay, it looks like B needs to be 3, a positive 3. And the omega we already found on the previous page with the K and the M square rooted. The omega was a 4. So we're in business. We can say, hey, here is the specific solution for this story. This is exactly how it's going to begin and then bounce from there on. It's going to be -5 times the cosine of 4t plus 3 times the sine of 4t. And I can graph that, right, and watch this thing bounce. I have to modify this here a little bit. It's going to be -5 times the cosine of 4 times time plus 3 times the sine of 4x. Now, when I first go and graph this, I'm not going to be able to see the whole thing unless I change my window here a little bit. Let's change this maybe, so instead of from -4 to 4, I've already seen this problem, so I kind of know how we should go with this. Maybe let's just go -8 to 8. We'll see how much this thing bounces. Okay, there it goes. It's bouncing. Okay, yeah, it started low, and it started with an upward velocity. It didn't start with a flat little spot on the bumps. It actually had an upward slope to it. And if I say, hey, can you calculate a value for me? Where are you at time 0? It says, oh, I'm at -5. Let's just check out the velocity. Calculate the derivative at time 0. It says 12. Okay, so it's doing what we want. It's got the right velocity, and it's got the right initial position. Now, the rest of this page, I want to show you some stuff that you're going to do in university. Okay, sort of after high school level stuff. So it's going to get a little intense here. I want to show you a way where you can find out where the top of this bump is without actually using your graphing calculator and without trying to do a whole bunch of calculus doing a derivative. There is a neat way that you can rewrite this. And what I'm noticing is when we blended the cosine and the sine together, and this happens every time they've got the same frequency, here they're both like a 4t, you end up with another sine-ish, cos-ish looking graph, a sinusoidal graph, we might say. And it's possible to rewrite this -5 cos 4t plus 3 sine 4t. You can write it as a single sine function. You can write it as an amplitude, d, times the sine of that 4t, but then what we call a phase shift. And what we're going to try to do is to see if we can figure out those values for d and for the phase shift. We already know the answer for the omega, right? So we already know that this is going to be the sine of 4t, but I'm not sure about the phase shift, which we're going to call the Greek letter phi. That just shifts it horizontally, and we don't know the value for d. So again, looking back at the calculator, yeah, I don't right now know the overall amplitude of this story. That's the d. Okay, capital D, and it does look like this graph has been shifted because sine should start right there. So it's been shifted a little bit in order to create this picture. Okay, well, let's see if we can figure out the values then for D and for phi. To do this, we're going to go through an interesting little technique that when the first time I saw it at university, I'll tell you, I must have like looked down to tie my shoe or something at the wrong time. I looked up And the professor was like 3 lines deep, and I was looking at it going, what is going on? And it took me quite some time to figure out what happened. So I'm kind of showing you this so that you don't have the same experience I did. I'm going to use this trig identity, and you might want to scribble that down at the top of your page up there. The one from Math 12 that says the sine of a plus b is sine a cos b plus cos a sine b. And I'm going to look at this d sine 4t plus phi, and I'm going to treat that kind of like that, well, not kind of like that trig identity up there. So we have some value right here that's behaving like the A, and some value there that's behaving like the B. And I'm going to rewrite that using that trig identity here just for a moment. And I'm going to then try to find D and phi. So expanding it out, it gets bigger and uglier before it gets better. Let's leave the D out front for a minute. Using the trig identity, you would have the sine of 4t, cosine of phi, and then plus the cosine of 4t times the sine of phi. So all I've done is use that trig identity up there at the top of the page and said, okay, 4t is A and phi is going to be the B. It's definitely looking messier than it did before, and I'm now going to maybe make it even messier. I'm going to distribute that D, but I don't have a lot of room to finish this off. So I'm going to kind of distribute the D, and I'm going to colorize it at the same time. If you happen to have some colored pens, this really might help you out. I'm going to rewrite this as, okay, for the first part, I'm going to put the D and the cos phi together. I'm going to distribute the D, and I'm going to write that deliberately here in red. So D, a number that I just don't know, multiplied by the cosine of phi. So phi is just a number I don't know, and cosine of phi is also a number I don't know. That would be multiplied by the sine of 4t. So I'm just distributing the D and then rearranging slightly. I'm trading the places of the cosine and the sine. Okay, moving on down the road. Same thing, distribute the D, maybe put the phi term out front, and I'm going to write this in green. This is D times the sine of phi multiplied by the cosine of 4t. And this is probably where I looked down my university class and totally got lost. And I didn't realize what my professor was doing was they were trying to make this line here look exactly like this line there. And they were saying, look, it's pretty much a match already. There's a term in there with a cosine of 4t, and there's a term with a sine, and there's numbers out front. And so if you look at it, that -5 that's sitting in front of the cosine, well, okay, here's a cosine of 4t with this green thing out front. So maybe grab your green pen and say, hey, look, this -5, that's the D sine phi. And that other term with the sine of 4t, it's got this 3 out front. Well, here's your sine of 4t term with this red stuff out front. So that 3 has got to be the red stuff. So it looks like we've actually got kind of a couple of equations for a couple of unknowns here. It's looking to me like D, some number I don't know, multiplied by cosine of phi, again, a number I don't know, that needs to be 3. And here's another equation. D times the sine of phi has to be -5. So it's 2 equations, 2 unknowns, and you're just going to try to find D and phi. The classic way to solve this one is to stack them and to put the sine one on top of the cosine one. And so you could say D times the sine of phi, well, that's going to equal -5. And then we'll stack that equation up on top of the red one. So down here we'll have D cos. You can see what's going to happen. We won't have to worry about the D's anymore. So the D's go away, and you end up creating this story where tan of phi is equal to -5/3. Okay, well, we can actually take our calculator And we can go and figure out what that is. I have to make sure I'm in radians. Pretty sure it was. Yeah. Okay, so I'm going to say, hey, calculator, can you untan negative 5/3? And it says, sure. Negative 1.0304. Okay. Now, where could I scribble this in? Maybe up in here. So now you can keep going and pick either one of those equations. Maybe I'll pick the green one and say d times the sine of negative 1.0304 needs to be negative 5. You go to your calculator. You say, okay, calculator, negative 5 divided by the sine of that answer. And it says 5.8310. Okay, so you've solved for these two numbers, the d and the phi. And you're probably, and justifiably, saying, so what? Like, what good is this? Well, here's the thing. Instead of writing this blue line at the top of the page, right, or the one, actually, let's go back up. Instead of writing the one up there at the top of the page, I can say, oh, here's a nicer way to write the answer. It's the same answer, but I could write 5.8310 times the sine of 4t minus 1.0304. So that's a little shorter way of writing what the answer is. Okay, yeah, sure, it's got some decimals in it, but it's a little bit shorter. And I'm just going to graph this, and as I do, start thinking about like, hey, well, how big will this graph ever get? Well, the amplitude's sitting right out front, right? So I'm going to leave that graph on there, the original one, and now I'm going to put in here, I'm going to put in this one, but I'm going to make it dark, right? So it's nice and thick. So this is going to be 5.8310 times the sine of 4, there's my bounce rate, times my time, minus 1.0304. Okay, so I already can tell you what the amplitude will be. It's going to get as big as 5.8310. Okay, and if I graph it now, you can see it just sits right on top of the old answer. So I haven't found anything new, but I've just got a new way of expressing it. In some ways, a much, much more useful way of expressing it. So if somebody asks me, well, what's the maximum position your bungee jumper, your bouncing mass ever gets to? Oh, it's so easy now. I can just say, hey, that's just the value d, the number out front. So the maximum position, it's just 5.8310 meters. What about the maximum velocity? Well, think about taking a derivative of this equation right here. This 4, that omega, would show up out front like a little party crasher, right, because of the chain rule. And you'd have that 5.8310 still sitting there, but then the sine would turn into a cosine. And so what happens is the maximum velocity, and we talked about this on the first day, it's just that omega, the 4, multiplied by the d. So you take 5.8310, you'd multiply it by 4, right? So basically we're taking omega, multiplying it by the maximum x that you ever saw, and that number ends up being 23.3238. Not that you really care. You shouldn't really care about this value, but you should care about how you can get there quickly. You can just take the maximum position and multiply it by the omega. And if you've done this method, you know the maximum position really quickly. The maximum acceleration, same thing. Take another derivative, and one more time a 4 shows up. Another omega crashes the party. So it's an omega times the d. And so you end up with omega squared times the x max. Or I guess another way to say it is omega times the v max. And that number, if you're curious, is 93.2952. That's an acceleration, so it would be meters per second squared. So that's kind of an extra topic just to allow you to get ready for the university way that you're going to deal with the harmonic oscillator equations. Let's try some, you can call this homework if you want. So I've called this guided practice, and I'm gonna challenge you to stop the video, try the question out on your own, and then keep playing the video just so you can see if you've got it right. Okay, so I'll explain it first, and then maybe hit pause and see what you think, and then we'll go from there. So this one says solve the differential equation. Looks like there's a second derivative. They've got s instead of x, whatever. It's the same thing. Plus 25s is equal to 0. So I'm going to, in this blank area here, see if I can find the kind of general solution for the story. And then once I have the general solution, then I'm going to go and find the specific solutions for all those parts there for part A, B, C, and D. So maybe pause the video and see if you can find just the general solution here first, the omega, and then we'll go and find the values for A and for B. Okay, so here I go, trying to see if I can get this thing to work. I'm going to move the 25s to the other side. It looks like s double prime. It's very common actually to use s for position in calculus. So this is a pretty routine thing to see in s there. Okay, well that's the same thing as saying s double prime is equal to negative k over m times an s, right, if this was our classic physics harmonic oscillator. So it looks to me like this k over m that we would have been playing with masses and springs must be 25. And the omega would be the square root of that. That just makes sure that we'll have the f equals ma to work out. So we're going to go square root of 25. Okay, it looks like the omega is 5. So speaking kind of generally for this solution here, it looks like the position, which varies with time, would be some number in front of a cosine. That number is really important for the original release position, right? So if you move the thing away from equilibrium, you'll have to have an a times 5t plus b times the sine of 5t. And that b is really important if you throw it, if you give it an initial velocity. And so once again, our plan, the a is equal to just the original position, and the b, well, actually omega times b is equal to the original velocity. So we can swing that around and say, oh, well, if that's true, then the b is just the original velocity divided by the omega. Okay, so now let's try out the individual solutions. Take your hand at each one, and I'll just do them A through B, but maybe consider pausing the video and saying, okay, well, what would the kind of simplified answer look like if I substitute values in? So take a moment and try out part A. So for part A, there's a mass on a spring, right? So there's like a ceiling, the spring is hanging, there's a mass there. It's at equilibrium, it's at x, oh, I shouldn't say x, I should say s. Oh, try that again here. See if I get that to come back. Oh, maybe not. Draw it up here. Ah, there it is. Okay, so there's s is equal to 0 right there. And in this story, it says, hey, let's begin by releasing it right from that position. Oh, and the velocity at the beginning, the velocity will be 0. So it's like you put your hand on it, you're holding it at the equilibrium position, and then you just let go. Well, nothing happens. Nothing happens at all, right? It looks like this tells me that A is equal to 0, and this story tells me that B is equal to 0. And so if A and B are 0, then there's nothing left. And then the story is, hey, guess what? This thing just stays at 0. It's good. The math has actually figured out what happens when you just have a mass on a spring at equilibrium and let it go. Nothing happens. It stays there. Okay, part B. We're going to start 4 meters up, but with no velocity. See if you can think about what the solution then would look like. All right, this tells me that A would be 4, and this tells me that B would be 0. Don't even need the term. So the solution here would be, oh, I'm always tempted to write x. The solution here would be the position at any time would be 4 times the cosine of 5t. That's it. Right? It doesn't, if I was to graph it, let's clear these ones off. for cos 5t. This one starts with an initial position but doesn't start with a velocity, and then it bounces away from there. Okay, try part C. Okay, for C, it starts at equilibrium, so A is equal to 0, but we're going to kick it. We're going to throw it down at -2. Well, remember that the -2, that original velocity, it actually works out like this, that omega b is equal to v naught. So it looks like the b would have to be -2/5 in order for this to work. So this solution, if that's how you launch your oscillator, if you have it at equilibrium but then kind of pluck it and force it to go away with this negative velocity, then the answer would be -2/5, -0.4, there's 2/5, times the sine of 5t. So let's try that and just see if it looks right. So -0.4 times the sine of 5t. So this should start right at the origin, but it's going to start with some velocity. Oh, it doesn't actually look very impressive. Let's zoom in on it a little bit. Didn't have a very big velocity here. Maybe we'll go like -2 to 2. Yeah, okay. So this thing starts at the origin, but then is kind of plucked downwards. And if we check out the velocity at the very beginning, it says, yeah, -2. Things are working well. Last one. Looks like it's got an initial position and an initial velocity. Okay, if you've tried it out, looks like on this one, the A is equal to -6, and then the B would be 8/5. Right? There's an omega there because of the chain rule. So this one, the oscillator would be -6 cosine of 5t plus 8/5, 1.6 sine of 5t. And this is one of those ones you could blend together into just a single sine function if you wanted to. So those are specific solutions, particular solutions, we might say. Last one on this second to last page of homework here says, see if you can find the general solution. So it's just general. It'll have a's and b's in it for 16 times y double prime is plus 25y is equal to 0. Take a shot at it and we'll see what you get. So I would rearrange that, and I would say, okay, y double prime would be equal to, okay, moving that 25y to the other side, I'm going to have a -25 on top of 16 times y. So this kind of has a feeling of like a negative k over m times the y. So it looks to me like k over m is going to be 25 on top of 16. Maybe the spring constant was 25 and the mass was 16, right? That could be possible. The omega is going to be the square root of that. So if I square root that, I'm going to end up with 5/4. Now, they're not telling me how we're going to launch it. Like, where are you positioning it? What's the speed? I don't know. They're not saying. So I just have to come up with a general answer here and say, well, it looks like the position as time goes by, hey, they're using y's this time, would be some number possibly in front of a cosine of 5/4 t, and then possibly some number in front of a sine of 5/4 t. Still a general solution because I don't know the specific values for A and for B. Okay, last one here. Let's see what we've got. It says a light spring has 2.4 kilograms of mass on it. So because it says a light spring, I don't have to worry about the mass of the spring. Right? This is one of those times where we kind of cheat, right? We're like, well, did you know that the mass of the spring matters? It does unless it's light, right? So we'll just call it like a physics spring. We'll say it has no mass. So a light spring, 2.4 kilogram mass hanging on it, has a natural length of 1.8 meters. Okay, great. That's just hanging there. That would actually be where x was equal to 0. An additional force of 4.8 newtons stretches it to a new length of 2.3 meters. Okay, sounds like in this story here, we've actually had it grow by a little bit, a change in x of 0.5 meters when we added that 4.8 newtons to it. Okay, the forces are moved before we allow it to oscillate. See if we can find the spring constant. Well, I know that generally F is equal to Kx in Physics 11. I'm going to say changes in F, if you add a little bit, will cause a little change in X. It'll deform the spring slightly. So we've seen an extra 0.5 meters. Oop, I have that backwards. Try that again. We've seen that if we put 4.8 newtons on it, then we end up with an extension of 0.5 meters. So if we divide, looks like we're going to end up with, well, it'll end up doubling that 4.8. We'll have 9.6 newtons per meter. So those are just little stories where they say, oh, let me just add a little force and you can see it stretch a bit. Then we'll take that force away before we do any of our oscillating here. But now we've learned that the spring constant is 9. Okay. Now we have to go and try to find the general solution. Well, to do that, we're going to need to know the omega. So we have the K, we have the M. I know that omega, the bouncing rate, is the square root of K over M. So it's going to be the square root of 9.6 all on top of 2.4. Okay, well that sounds like it's going to be a nice number. Double checking. Yep, that's a 4, all right. So we've got the square root of 4. We've got a nice healthy 2 for our bouncing rate, 2 radians per second. General solution, this thing could bounce like this with some sort of number out front of a cosine, because you might have an initial position when you let it go, and then some number in front of a sine, because it might have a velocity when you let it go, if you choose to do that. Okay, here's what's going to happen. We stretch it to a new length of 2.2 meters. Well, hang on. How long was it when it was just normal? Oh, when it was just relaxed, it was 1.8 meters. So we're stretching it to 2.2 meters. You pulled it down. You pulled it down by 0.4 meters, it sounds like. So that information is telling me, yep, the A, it's going to be down by 0.4 meters. Oh, and there's this velocity of 6. Well, remember that for velocities, omega times b is equal to the original velocity. So it looks like 2 times b is equal to 6. Looks like the b is going to equal 3. Okay, so find the specific solution for this story. Yep. Oh, I was using x. Whether you use x or s, it doesn't really matter, right? So x, s, whatever position, looks like it's going to be negative 0.4 times the cosine of 2t plus 3 times the sine of 2t. Okay, see if you can find the position at time 12. I'm just going to do this one on my graphing calculator, right? And then we'll do a little more heavy-duty work with it in a second. But if I go negative 0.4 times the cosine of 2t, so it's not bouncing super fast, plus 3 sine of 2t. Okay, so I'm using x's for t's. 0.4, negative 3. Yeah, that looks good. Let's see how this thing looks. Okay, it's going a little bit off screen there. Looks like it's bouncing fairly slowly. I'm going to have to change things here a little bit for my window just to make sure I can see everything. So window, let's go, I don't know, maybe negative 4 to 4. So you can see it starts with a really small initial position, not very much there. Now, this is actually This is actually one of those times where the physics teacher didn't quite get the story right. Just so you know, this amplitude of bounce looks like it's a few meters there, right? About 3 meters. That wouldn't work with a spring that's only 2 meters long. So, you'd have to go, you wouldn't have to change too much in the story, but you might have to say, oh, I'm sorry, did I say that the natural length was 1.8 meters? I'm going to edit this here now because it doesn't quite make sense. I meant to say 11.8 meters and 12.3 meters here. And, oh, down to 12.2 meters, right? So now it's long enough. Now it's fine. Okay. All right, so the position at time 12, well, I'll have to go farther down the road, I guess, won't I? Change my x's so that I get out to at least 12. Let's change it to 15. Okay, so here it is bouncing away. It's going to take 15 seconds to get off the edge of the screen here. If I wanted to find out where it was at time 15 or time 12, I can go calculate a value at time 12. And it says, okay, yeah, I got a number here for you. Looks like it's going to be at some position S at time 12. It's going to be negative 2.8864 meters. What about the velocity at time 12? Well, just looking at the graph there, it looks like it's starting to go back uphill. Let's find out for sure. So I can calculate number 6, do a derivative at time 12. Yep, we're going back uphill. Not super fast though. So the S prime, the velocity at 12, 1.8206 meters per second. Okay, now the challenge. Can you convert this into a single sine function? It's possible, right? It is actually possible to do it, right? We can take that equation that's up there at the top of the page, and we'll see if we can, rewrite that in a way where it's like a d times sine of omega t plus a phi. So I'm kind of looking back at the last page that we were working on, and we said, oh, okay, well, you could say that your xs, whatever you want to call it, could be, what did we say? We said it was d cosine of phi times the sine. Here it would be of 2t. And then there was the green part, plus d times the sine of phi times the cosine of 2t. This is the hard part. So looking back at this story here, the green thing is the stuff in front of the cosine, and the red thing is the stuff in front of the sine. Okay, well, if we stack one on top of the other, we could say that d sine of phi on top of d cos of phi, that would be just tan of phi. That would have to be, all right, that's got to be the green thing, negative 0.4, all on top of the red thing, the 3. Okay, so I'm going to take my calculator and say, hey, calculator, you got to help me out here. I need to do the untanning of negative 0.4 divided by a 3. Okay, it looks like that phase is negative 0.1326. And now I'm going to grab one of those equations, maybe the green one here, d sine phi has to equal that negative 0.4. So if I go negative 0.4 divided by the sine, okay, looks like d needs to be 3.0265. So here's an option. To be honest, it's a better option. You could say the position at any time. You don't have to tolerate this blend up at the top of the page here of cosines and sines. You can write it that way if you want, but it's okay to say, well, how about I write that as being 3.0265 times the sine of 2t minus 0.1326. And that story kind of has everything nicely packaged into it. And if somebody says, well, what's the maximum position? You want to know the maximum position? It's the amplitude on this math 12 sine function. There's your maximum position, 3.0265. And then if they say, oh, well, what's the maximum velocity? Right? This is actually pretty easy. The Vmax, it would actually just be omega multiplied by xmax. So it's that 3.0625 multiplied by your omega of 2. Okay, looks like Vmax here would be 6.0531. And then they're like, oh, well, what's the acceleration? Yeah, no problem. It would just pick up another omega. So Amax would just be omega squared times xmax. Every time you do a derivative of that purple equation there, the 2 pops out from the chain rule. So we would get another 2. So it looks like it's 12.1062. So the units here, this would have been expressed in meters. This would be meters per second and meters per second squared. I just wanted to show you that d sine omega t plus the phase shift thing, because it's definitely something you'll see in university. And well, my experience was the first time I saw it, it was pretty darn confusing. And so I wanted to just give you a little bit of a heads up on that. This worksheet is one of the 2 final assignments for the course. I think it's actually probably going to take you about 10 minutes, just depending on your music counting skills. And if you're in music or band, it may actually be harder to do this than if you're not, just because of your temptation to start on one. But you're going to pick your own song and see if you can tell me how much mass I should put in that can of water. And I will try it out and I will film it and then put the video up online where you can see whether or not you've got it right or not. And you have to just keep trying it till you get it right. Most people get it first try. The spring constant is the same one that I used. So for your calculations here, the number that you'll want to use for the K is 15.35 newtons per meter. And you will, because this is real life, you'll want to factor in the mass of the spring. You'll have to include 1/3 of the mass of the spring. Be careful with grams and kilograms here. I had a chemistry scale, so it's in grams. The full mass of the spring is 65.57 grams. Move that 3 decimal places if you want to have it in kilograms, and take 1/3 of it, right, for our calculations. Now, when you're counting the music, I would suggest that you go for something around 50 beats, okay? At least 40. 50 is better. 60 is even better again. And you have to take a stopwatch, and you're going to have to time how long it takes for those 50 beats to happen. Here's where it gets interesting, right? It's all about making sure you start at the right time. So you're going to have your music rolling, and then you're going to need to start your stopwatch on your phone at just the right time. But you have to start on 0. So if the music is sitting there going like this, it doesn't work to go, okay, 1, 2, 3, 4, 5, like that. You might be tempted to do that if you're in band, right? Because you would often start your song on beat 1. Instead, you're going to have to do this. You're going to have to take your stopwatch and go 0, 1, 2, 3, 4, and keep going until you get to like 49, 50, and then you can stop. And you're going to want hundreds of seconds. And you're going to probably want to do it a couple of times. until you're pretty darn sure within just a few hundredths of a second that you've actually got it right. If you're having troubles knowing like how to start, like it feels awkward starting, do the old NASA thing and you can sit there and go, okay, the music's rolling and you can go 3, 2, 1, 0, 1, 2, 3, and then 48, 49, 50 when you stop. Try that out a few times though on your song, and you can do your calculations to tell me how much mass the whole thing should be. It's the mass of the can and the water, so I'll put the water in until the can and the water hit that right amount. And then you can see if you've got that right. That's actually not an assignment you need to be working on right now, unless you're looking for something to do. There's going to be a lot of time, not next week, but the week after, where you can polish that off. But if you wanted to get it out of the way, you certainly could. And that marks the end of actually the first half of this extra little unit on harmonic oscillators. Next time, we're going to take a look at what happens if there's friction involved and the motion starts to die away.